Hi everyone, welcome to CHEM. Now today's video is on covalent bonding part 7 video, and here we are going to deal with resonance, and this will be the last video of covalent bonding. So before starting, already 6 videos are uploaded in channel, you can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to CHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. Here we are going to deal with different examples of resonance. So for SO4 2-, the resonance will be just like this. The structure should be near about like this. That is a sulfur in between. O-, here also another O-, and there is a double bond oxygen, another double bond oxygen. And we have already derived this structure using VSEPR theory, right? So if you consider here the resonance structure, it would look somewhat like this. That is, this sulfur has an oxygen with a lone pair like this, and the other pairs are there. Extra lone pair is present in this oxygen. Similarly for this one also, there is extra lone pairs and minus here. Here is a double bond oxygen and double bond oxygen. What happens is that the electrons present here comes to this bond, and the electrons of this bond goes over this oxygen. Ultimately, we get another type of resonance structure which looks like this, where this is O-, this is double bond oxygen, and this will be O- with another double bond oxygen, and this exchange will continue and there will be more or less many resonance structure. So from here we can derive an average molecular picture which looks like this. That is, we have a sulfur in between, oxygen and the other oxygens have a single bond for permanent, and there can be double bonds which breaks and makes during the process of resonance, right? So the overall charge over SO4 will be 2-, right? Now we will see for CO3 2-. See this very carefully. We know for carbon it is 4 plus 3, 1 minus 1 plus 2 gives us 6, that is planar trigonal in structure, and it would look like this. That is carbon with a double bond oxygen, another carbon with a O- and another carbon with a O-. So here is an extra pair of electrons. Now this electron will jump here in this bond to form a double bond, and this bond pair will go to form a lone pair. So what we get ultimately is like this. That is carbon, double bond oxygen, oxygen minus, oxygen minus here. Again same thing, that is, suppose this lone pair comes here and this opens up. So we will get another structure, O-, this is O-, and this will be double bond oxygen. Similarly, the last structure which we can get another sort of structure, which is, that is, this can open up. So you have to understand that if this opens up, then carbon is in shortage of 2 electrons and this oxygen is in gain of 2 electrons. That is, it is in profit of 2 electrons. So the structure ultimately which we get is like this. That is, carbon is having a positive charge. Here is our O-, similarly here O-, and here also O-. And these structures will be numbered in order to understand their contribution in the resonance. So this is 1, next one is 2, this is 3, and this one is 4. And all these resonance structures should be drawn within a third bracket like this. This will be proper way of representation. Now we will see the rules for contribution of canonical forms. Now the structure which has maximum number of covalent bonds should be more stable. So from here we can understand that since structure 1, 2 and 3 is having maximum number of covalent bonds, so these are more stable than structure 4. Next point is that for a given set of canonical forms having same number of covalent bonds, the one where negative charge is more over electronegative and positive charge over more electropositive element will be more stable. What it states simply is that the electronegative atom should contain the negative charge, whereas the electropositive atom should contain the positive charge to be more stable. And the last point states that if the like charges are far away from each other and unlike charges are close to each other, then the canonical form will have higher contribution. So the canonical form will have higher contribution. Similar charges are away from each other and the unlike charges, that is dissimilar charges, are closer, that is positive and negative are closer to each other. So let us see. This is a question, that is we have to explain why carbonic acid is less stable than CO3 2-. As we have already seen the resonance structure of CO3 2-, now we are going to see the resonance structure of carbonic acid. Now what is carbonic acid? This carbonic acid is H2CO3. So it can be drawn like this: carbon double bond oxygen, and these two oxygens are occupied by hydrogens. Now this oxygen also has lone pairs, it can be donated and this opens up. What we get is like this structure, that is carbon having double bond oxygen, and here is a positive charge coming up, here is a negative charge coming up. Similarly here OH, right. Next we can see that carbon, oxygen minus, next this lone pair can participate and this can, this can participate and gives up. So ultimately we get is OH, here is a double bond OH plus, and again it undergoes resonance to form this kind of moiety. That is, here will be positive if this opens up, and here will be OH and another OH from here, right. So this is the resonance structure for carbonic acid, and this is important, right. So if we name this as A, B, C, D, then from the rules we have understood that A will have the maximum contribution and the D will have the least contribution, as there is separation of charges positive and negative, right. And the number of covalent bonds is also less for D and maximum for A. And A has no charge separation, so it is better option. So B and C will have equal contribution. So from here we can understand that for carbonate, as we have seen, it is evident that structures 1, 2 and 3 are highly contributing. If you focus on the previous case, we have already seen 1, 2 and 3 are highly contributing, right. So it is evident that it is for this reason that the charge cloud delocalization is extensive, that is the electrons are displaced extensively, accounting for greater stability. It is evident from the canonical forms of carbonic acid that the structure A is highly contributing. As we have seen that for carbonic acid, A is highly contributing and D is least contributing. B and C low, since the positive charge is present over electronegative atom. Also, due to the structure D, it will be weakly contributing due to lesser number of covalent bonds, and thus the resonance stabilization of carbonic acid much lesser, and since the electron cloud delocalization is weaker, so carbonate is more stable than carbonic acid. So this B and C is having, also we can see that oxygen being electronegative, it is having a positive charge. So the contribution is decreasing for these resonance stabilized structures. Next is BF3. We will deal with BF3. This is also trigonal planar in nature. So this has B, F, F and F. F also has lone pairs of electrons, and these lone pairs are being donated, right. So fluorine will now have a positive charge over it. So here we have a double bond fluorine, positive charge, and here a negative charge. So from here only you can understand that fluorine being electronegative atom is having a positive charge, right? So it will have a lesser contribution. But here the next or the foremost thing to be considered is that the covalent bonds, because the first criteria is fulfillment of covalent bond. So the first structure, which is 1, is having the least covalent bond. So its contribution is much less. Then the next criteria is being considered. So from here only you can understand that here the number of covalent bonds is less. So number of covalent bonds is less means that this will be least contributing. Though here electronegative atom is containing a positive charge, but the first criteria is having maximum number of covalent bonds. So ultimately what we get, the order is 2 is equal to 3, which is equal to 4, and this is much greater in contribution than 1, right? Now we will see for ozone. Now ozone is also planar trigonal in nature. So it will have a structure like this with lone pairs. This is the oxygen and here is O minus. So here is a lone pair, right? And here is a plus charge. Similarly, what happens is that this electron comes here and this electron moves out. So we get another structure which looks like same, but the double bond is in the different side. So here we have a double bond and here we have a single bond, right? And here is the positive charge. Next, what happens is that this bond is being donated to this one and we get a structure like this. That is oxygen having 2 lone pairs and this O minus and this O plus. Again, this can be from the opposite end only. What happens is that this is given up and here it comes. So this one will become negative and the structure will be like this. Here will be our positive charge and here will be our negative charge. And if we number the structures, it will be 1, 2, 3, 4, right? And the contribution will be 1 will be having similar contribution to 2 because the number of covalent bonds are same, whereas for 4 and 3 the number of covalent bonds is much lesser, so it will have least contribution, right? So these are 1,3 dipolar structure. Now if someone asks you a question, that is you have to explain why ozone will have finite dipole moment. So this can be explained by drawing an average structure of ozone. This will have 2 lone pairs, but since we are drawing average structure, so 1 lone pair will be considered. Here will be 1 bond and the double bonds are being formed and again broken. So here is a delta positive, here is a delta negative and here is a delta negative. Here will be a greater dipole moment. Similarly, here also there will be a greater dipole moment, but from 2 sides. So the net dipole moment will be towards this side. So let us see. We can tell that from the canonical structures 1, 2, 3 and 4, we have an equivalent structure like this. Okay. The 2 bond moments along the 2 oxygen-oxygen bond, which we see here and here, are vectorically added to give a resultant moment, and this moment is somewhat reduced by the moment due to the lone pair. Hence, the molecule has a dipole moment which is finite, which is towards this side, right? Now we will see another example, that is NO2. NO2 also has a finite dipole moment and this can be explained in the same way. 7 plus 2, 1 minus 1 plus 1 equals to 8, which is a tetrahedral structure, right? So here we can draw it like this: nitrogen, double bond, O minus. This will resonate to form nitrogen, lone pair, O minus, double bond here. Similarly, there will be a positive charge on nitrogen. So nitrogen positive, O minus and O minus, right? And if we number them, then this is 1, 2 and 3. And from here we can understand that 1 and 2 has same number of covalent bonds and the number is much greater than 3. So this will be the contribution. And if we try to draw the equivalent structure, it will be like this. Here is oxygen, here is oxygen, and these bonds are temporary, delta minus and delta positive here. And about the dipole moment, here is a moment towards this side. Similarly, there are two moments on the nitrogen oxygen bonds, and ultimately the net finite dipole moment is towards this side. Now we will see the most important question, that is, we have to explain that sodium azide is more stable than hydrozoic acid. Now what is sodium azide? We will generally focus on the anion NaN3, and we will focus on the structure of N3 minus. If you see here, it will be 7 plus 2, 1 minus 2 equal to 4, and we have already done its structure to be as linear, right? So it will look like this: nitrogen, double bond, nitrogen, double bond, nitrogen. This is one of the structures. Here nitrogen is positive and here nitrogen is negative. Similarly, another structure can be drawn which is having nitrogen with triple bond nitrogen. Here is a positive charge and here will be a 2 negative charge present over this. What happens is that if you focus, this is being donated here and this opens up, right? If we contribute to the next structure, which can be like this, that is, here nitrogen will have similarly 2 minus, then here nitrogen positive, here is a triple bond nitrogen. Another structure which can be drawn from here is like this: nitrogen, here double bond and nitrogen, right? Again, another structure from here which can be drawn is nitrogen with 2 lone pairs and N, here is nitrogen positive. That is, this bond has opened up towards this side. Similarly, another last structure which we can draw is nitrogen with 2 minus and then nitrogen positive, and here is nitrogen. So here we have lone pairs. If we number them, then we can see that there is many structures, resonance structures. That is 1, 2, 3, 4, 5, 6. 6 resonance structure. And we will also see for hydrozoic acid, right? So if we try to see the contribution, see that 2's contribution is much greater than 1 and 3. Next comes our 6, then comes our 4 and then comes our 5. So among all the above canonical forms, 1, 2, 3 will be more contributing due to the greater number of covalent bonds. 2 will still have higher contribution since 2 negative charge is furthest apart. If you can see, the 2 negative charges are furthest apart. And positive and negative charges are close to each other in structure 1 and 3. As a result of which, there will be equal contribution and will have lesser contribution than structure 2. Now if we consider for N3H, if you can see, if we consider for N3H, then it will look like this. That is, here will be double bond, here will be double bond, a hydrogen will be present, here is our lone pair. Similarly, here is a negative charge and here is a positive charge. And if we see here for this one, then here there can be triple bond, here can be hydrogen, a positive charge, here also a positive charge and here 2 negative charges, right? And another one can be like this: nitrogen having hydrogen, nitrogen with a positive charge, here is the 2 lone pairs, triple bond N, and this can continue. but from the structures only you can understand the contributions will be extremely low. Extremely low. Because here two positive charges are present. Again here is an unequal contribution of the charges present. So in N3 minus structure 1, 2 and 3 will have higher contribution. But for N3H, that is hydrozoic acid, only structure 1 and 2 will be highly contributing. The structure 3 will have weaker contribution since the positive charges as well as the negative charges are very close to each other. Thus, the extent of delocalization in the hydrozoic acid is weaker compared to N3 minus, and thus hence N3 minus is more resonance stabilized than hydrozoic acid, right? The last example is cyanate ion. So cyanate ion looks like this, NCO, right? So it will look like this. This is our structure 1. This will undergo resonance to form N minus double bond C double bond. This is our 2. Next will be N minus double bond C plus O minus. And this is the 3 structures of cyanate ion. So here ends the topic of covalent bonding. I have covered all the topics necessary from my side. If you have any kinds of doubt or if you require any kind of video lectures on particular topics, you can say me in the comment section. So this much for today. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.